Welcome back to the Deep Dive. Today we're looking at one of the biggest accepted truths in AI.
This idea that to get really powerful logical reasoning, you just need more and more parameters.
You know, the kind of reasoning it takes to solve complex math problems or win at competitive coding. The consensus has always been that this is a game only for massive models.
We're talking 671 billion, even over a trillion parameters.
But that's the very idea we're here to question.
We are, because we're diving into a new paper from Sino-Weibo Inc. on a model called VibeThinker 1.5B.
And the 1.5B is the key part of that name. It's tiny, just 1.5 billion parameters.
But the claim is that this compact model has better reasoning skills than giants like DeepSeek R1, which is, what, hundreds of times larger?
So the central question for you listening is pretty clear.
Yeah.
How on earth did they do that? How do you get large model results without the large model?
And the answer isn't some new chip or hardware. It's a really clever post-training method they call diversity-driven optimization.
Okay, so to really get this, we should probably set the stage. What's the standard playbook right now?
Well, the current paradigm is what's called the Large Reasoning Model Approach, or LRM. You can think of OpenAI's O1 model as one of the pioneers here.
Right, they use things like long chain of thought and reinforcement learning.
And that really established the main strategies everyone started using: RL scaling and test time scaling.
Which in turn led to this arms race for size.
It did. It gave us DeepSeek R1 at 671 billion parameters, Kimi K2 at over a trillion. The thinking became very rigid. More parameters equals better reasoning.
So VibeThinker 1.5B is, it's a direct challenge to that. It's proof that a much smaller model can have these, incredible reasoning abilities that we thought were out of reach.
And think about what that means. A drastic reduction in the cost to train and run these things. It could open up high-end reasoning to so many more people.
But they couldn't just follow the old rules to get there. They needed a new philosophy.
They did, and that philosophy is at the core of their work. They call it the spectrum-to-signal principle, or SSP.
The spectrum-to-signal principle. Let's break that down.
So it redefines the whole post-training process. It takes the two main stages, supervised fine-tuning, SFT, and reinforcement learning, RL.
And it gives them very different jobs.
Very different, but synergistic jobs, and it's a two-phase approach.
Okay, so what is phase one? What's the role of SFT in this new world?
Phase one is the spectrum phase. And this is a bit counterintuitive. The goal of SFT is not to find the single best answer.
Not accuracy.
Not at first. The goal is to maximize the model's output diversity.
How do you even measure that?
They use a metric called pass at K. So instead of pass at 1, which is just, is this one answer correct?
Yeah.
Pass at K asks, out of K different answers the model gives, is at least one of them correct?
Ah, okay. So SFT is being trained to brainstorm, to generate a broad spectrum of possible solutions.
That's the perfect way to put it. It's cultivating breadth. And only after that do you move to phase 2.
Which is the signal phase.
Right. And this is where reinforcement learning comes in. Its job is to look at that broad spectrum of answers that SFT created, find the correct signal within it.
And then amplify that, make the model more likely to produce that winning pathway.
Turn up the volume on the right answers that are already somewhere in the mix.
Okay, so SFT populates the search space, and RL refines it. But if the SFT phase is designed to be so diverse, I have to imagine it's also creating a lot of noise, maybe even wrong answers.
It is, and that's the challenge they had to solve. How do you make the RL stage efficient?
What's the method?
It's called two-stage diversity exploring distillation.
Let's get into that. What's the first stage?
The first stage is domain-aware diversity probing. So for something like math, they don't just treat it as one big subject.
They break it down
into subdomains. Algebra, geometry, calculus, statistics, you get the idea.
Okay, so they've got these different buckets of knowledge.
And as they're fine-tuning, they keep saving checkpoints of the model. Then they test each checkpoint on each subdomain using that pass at K metric we talked about.
So they're looking for the checkpoint that is the most diverse for algebra and another one for geometry.
You've got it. They're finding the specialist checkpoint for each domain, the one that's best at generating lots of different potential solutions for that specific area.
So you end up with a team of these specialist models. How do you bring them together?
That's stage 2, expert model fusion. They take all those specialist checkpoints and merge them into a single SFT model.
No.
It's actually a pretty straightforward, unweighted linear combination of the parameters. And what's amazing is that this final merged model is great at both It has a high pass at K, so it's diverse, but it also has a high pass at 1, meaning its top answer is usually correct.
So by training for breadth, they accidentally reinforce the best single paths.
It seems so. It creates this perfect, rich foundation for the RL phase to work with.
All right, so that brings us to the signal phase.
Yeah.
The toolbox is built. Now the model has to learn which tool to use. And the framework here is MaxEnt-Guided Policy Optimization, or MGPO.
And this is all about efficiency. It's about focusing the training effort where it will have the most impact.
And their core idea, their hypothesis, is that a model learns best when it's most uncertain.
When it's most uncertain about a problem, yes. That's what they call the critical learning frontier.
And how do they define that point of maximum uncertainty?
Well, for a problem where the answer is either right or wrong, maximum uncertainty happens when the model's chance of getting it right, they call it PX&E, is about 0.5.
A coin toss.
A coin toss. The model isn't clueless, but it's not confident either. And they argue that's the perfect state for learning. The problem is not too hard, not too easy.
So the goal is to find all the 50-50 problems and just hammer away at those. How does MGPO do that?
It uses something called entropy deviation regularization. Basically, it measures how far away a problem's current success rate is from that ideal 0.5 sweet spot.
And they use KL divergence for that measurement, right?
They do. That gives them a number, a distance. And they use that distance to create a weighting function, all ME.
So problems where the model is at that 50-50 point get the highest weight.
The highest weight. And that weight is then used to adjust the learning process, specifically the advantage term in their policy optimization objective.
So it's like an automatic curriculum. The system itself figures out which problems are the most valuable to practice right now.
That's a great summary. It focuses all the gradient updates on the problems where the model is most on the fence, which is a massive efficiency gain.
And it seems like it really, really paid off. Let's talk about the results. Did this little 1.5 billion parameter model actually stand up to the giants?
It did more than stand up. On complex math benchmarks, it beat them.
Let's hear the numbers.
Okay. Compared to the 671 billion parameter DeepSeek R1, VibeThinker got an 80.3 on the AME24 test. DeepSeek got 79.8.
It was a small win there.
It gets better. On AME25, VibeThinker scored 74.4 versus DeepSeek 70.0. And on HMME25, it was 50.4 for VibeThinker and only 41.7 for DeepSeek.
Wow. And you have to remember the base model they started with, its score on AME24 was just 6.7.
It's an incredible improvement. And it's not just math. It did really well on coding, too.
The LiveCodeBench benchmark.
On V6, yeah. It scored a 51.1 that just edged out a competitor, Magistral Medium, but the base model for VibeThinker scored 0.0 on that test.
0. That's quite a jump.
It really is.
Okay, this all sounds amazing, but what about the cost? This kind of advanced training can't be cheap.
Well, this is maybe the most shocking part. The total compute cost for all of this. SFT and RL was less than $8,000.
And under $8,000. To get results that beat a model, that must have cost
a lot more. The post-training for DeepSeek R1 was estimated at $294,000. For another model, Minimax M1, it was over $500,000.
So VibeThinker did it for, what, 130th or 160th of the cost? That's a huge deal.
It is, but we should be clear about where it still falls short.
Right. There has to be a trade-off for being so small. Where did the limits show up?
It seems to be in general, broad knowledge. On a benchmark called GPQA Diamond, which tests that, VibeThinker scored 46.7.
And the big models?
They're still 20 to 40 points ahead. So it seems this optimization technique is fantastic for structured reasoning, but the small parameter count does still limit its ability to store, a world's worth of facts.
Okay, whenever we see a small model make a huge leap like this, the first question people ask is about data contamination.
The did they cheat question.
Right. How do we know the answers weren't just in the training data?
The team was very aware of this. They ran pretty rigorous decontamination procedures. They standardized all the text, pre-processed it, and used 10-gram matching to find and throw out any training data that looked too similar to the test questions.
But the real proof, the smoking gun against contamination, is all about the timeline.
It is. This is the most convincing piece of evidence. The base model that VibeThinker is built on was finalized in September of 2024.
Okay.
But VibeThinker did really well on the AME25 and HMMT25 tests. And here's the thing. Those tests weren't released to the public until 2025.
So it's impossible for the answers to have been in the training data.
Impossible. The timeline just doesn't work. It proves the model is actually generalizing, not just memorizing. The results are legitimate.
So when we put this all together, what's the big takeaway for you listening to this? I mean, for me, it's that smart algorithms can matter more than just raw size.
At least for these kinds of reasoning tasks, yes. This work shows that if you first maximize diversity with SFT, then efficiently optimize with a method like MGPO.
You can unlock some truly powerful reasoning in a small, efficient model. It really challenges that whole scale is all you need mantra.
It absolutely does. It's a reevaluation of how we should approach building these systems. But, and this is the thought I want to leave you with, that big performance gap on the general knowledge test, GPQA Diamond.
Right, it's still there.
It's still there, and it points to the next major hurdle. The reasoning part might be solvable with clever algorithms, but figuring out how to pack broad world knowledge into these compact models, that remains a huge open question. And solving it is probably the key to their widespread real-world use.